Do you want your robot dog to follow you automatically and assist in your work when you are too busy to control them? If so, how can the dog figure out where to find you and walk to you without any collision along the way? Here, our team from Zheng University developed a mobile system which is exclusive for quadruped robots and can finish this pedestrian following task. First of all, the robot must locate your temporal positions. This can be achieved by an object tracking algorithm. Most of present tracking methods are based on deep learning techniques requiring a high-standard hardware configuration, which is not suitable for an onboard robot platform. Therefore, we propose a robust LiDAR-IMU-based single object tracking algorithm, which is lightweight and insensitive to collisions. Well, for a specific category like humans, its shape and size remain relatively constant at different moments. So we can draw a point with a bounding box centered on it to define our target pedestrian. After this, we use min-cut algorithm to segment points in the bounding box. We build a 3D point graph using hierarchical KNN and define weighted edges and solve this graph cut problem by min-cut. And by comparing the size of the foreground and the background points, we can obtain the target as points belong to the object to account for the main proportion. Well, it's normal that some points will move off the bounding box between two time steps. During such time, our iterative tracking procedure begins to work. We repeatedly use the center of the segmented points in the previous frame to replace the center of the bounding box to make them finally align with each other again. But this move requires high real-time computation and it needs several processes. And it further proves that our method is fast and suitable for limited computational resources. Well, as quadruped robots can make a large instantaneous rotation around the axis, our bounding box will have an obvious offset on the x and y plane. This disturbance will cause damaging tracking failures. As we all know, inertial measurement unit can provide sequenced angular measurements between two LiDAR sweeps, so we integrate the measurements to compensate the displacement caused by rotation. To validate the performance for our LiDAR-IMU SOT method, we rotate the robot platform at an angular velocity up to 4 radians per second and compare the effects with and without IMU improvement. It's clear that under this circumstance, the one without IMU measurement loses the target, while the IMU-aided version can maintain a high robustness. So using tracking technique, robot can obtain the pedestrian's location, but this is not enough for the navigation directly, because the robot must know where it is and how its surroundings look like, so it can figure out walkable areas towards the pedestrian. But this is done by obstacle detection block. We use the off-the-shelf SLAM method, providing a local map as its input, and detection block returns a traversability cost map. Of course, the pedestrian's location will move to the local coordinate as a result. This is a glimpse of our traversability cost map. We use Grid Map Library to create a 2.5D point map by estimating terrain traversability through 3 characteristics in each 2D bird's view grid. The roughness R, the slope S, and the step height H. As cost increases, the probability of this grid being treated as an obstacle is higher. So now the robot gains the walkable area and the pedestrian's location. Finally, the robot can use the planning module for searching a path leading it to the pedestrian. In order to pass through narrow spaces, the footprint of quadruped robot is represented as a rectangle. With this footprint configuration, we can add constraints for the forward translational, lateral, and rotational velocity respectively. And then we treat the trajectory generation as an optimization problem, taking the kinematic constraints into account, and solve it in a cost-effective manner using nonlinear programming. We conduct some experiments in the real world. The equipment mounted on the quadruped robot is shown on the left, and the right side shows some examples of our indoor experiment. Note that due to the high mobility of the quadruped robot, it can be allowed to walk over some small height obstacles, circled in red, where omnidirectional robots may get stuck. We also process some outdoor experiments. That's all, thanks for watching.